So we left off, we did the revolution stuff, right? Okay.
The last thing we did was a funnel thing.
Okay. So the rest of the section is basically doing some Calc 3 stuff that we've seen previously, but now applying it to parametric surfaces. So we'll talk about partial derivatives real quick. Oh, well that's fun. Thank you. Partial derivatives. Vector valued functions. So we've already talked about R of uv, how we can define that in terms of x of uv, y of uv, and z of uv. Well, we could also write that as a vector valued function and we can take partial derivatives. And these aren't that complicated. It's exactly what you would expect it to be. When you take the partial derivative of x with respect to u, you get exactly partial x, partial u. Here you get partial y, partial u, and then partial z, partial u. And similarly, here you get partial x, partial v, partial y, partial v, and partial z, partial v. Okay, so those aren't horrible to work with. So now as far as like what they represent, so here's a picture. So let's say we have a U curve and some V curve. And then at this point, we find partial R, partial U. And that looks something like this. Okay, so partial R, partial U will just be tangent to the U curve at that point. And then similarly, partial R, partial V will be tangent to the V curve at that point. So that's what that looks like geometrically. Now, what do you suppose would happen if you took the cross product of partial R, partial U, and partial R, partial V? You'd get a normal vector. So let's pull out another color. It looks something like this. That would now be normal to some tangent plane at that point. So for that tangent plane, the normal vector would just be the cross product of the two. Does this make sense geometrically? Okay, so you got your U curve, your V curve, you find partial R, partial U, that represents tangent line or slope of tangent line in that direction, and so on and so forth. Cross the two vectors, you get a normal vector to those two. That would be a normal vector to a tangent plane at that point. And then there is a thing called the principal normal vector. I'm sorry, the principal unit normal vector. There's really, I suppose I didn't have to tell you what this was because you could have figured it out on your own, but the normal vector is partial R, partial U crossed partial R, partial V. How do I make it a unit vector? Divide by the magnitude, right? So this would be the definition for the unit normal vector, the principal unit normal vector. Okay. So let's do one example tying all this together. And then we'll tie it to one other Calc 3 thing that we've done. So let's say we want to find an equation of the tangent plane
Wait, is the principal unit normal vector also an n?
Well, yeah, I guess let's go make it a little subscript to make it clearer. I like that. Okay, so the principal unit normal vector, we can put a little subscript u so that we can differentiate it between any other normal vector. Okay, so if we want to find the equation of the tangent plane of the surface where x equals u squared minus v, y equals uv, and z equals v, when u equals -1 and v equals -2. Okay. Do you guys remember tangent plane equations? Hopefully. What do we need for a tangent plane equation?
A normal vector and a point.
And a point. Good. So, what do you want to find first? Okay, so what would the point be? Plug in -1, plug in -2 into x, y, and z, right? So that would correspond to what point? 3 for x. What's 2? -2. So that's the point when you plug in -1 into x, y, and z. So now we just need a normal vector, and in order to find a normal vector, we must find the partial derivatives with respect to u. So partial r partial u would be what? Just go component by component, right? 2u, yep, yep. Still on the screen? Yes, okay. And then partial r partial v would be? Good. Now, to make life easy, we already have a condition, right? We want u to be -1 and v to equal -2. So at u equals -1 and v equals -2, these become what vectors? Plug in u. You mean -2 and then -2, 0. And this one would. Okay. So these are the two normal vector, or the two partial derivative vectors. And now to find the normal vector, we must do the cross product of those two. So the normal vector would be the cross product of -2, -2, 0, -1, -1, 1, which gives us what vector? -2, yep. 2. Yep. So we have everything we need, right? We got our normal vector, so now our tangent plane would be -2 times what? X minus, what was our x coordinate? There we go. Plus 2 times y minus 2, and lucky for us, there's no z. So in this case, here is our tangent plane. Okay? Yes? Because the component for z was 0, so it'd be 0 times z minus 1, or z plus 2. Other questions? Okay. So the last thing we're going to do is tie surface area to parametric surfaces. So anybody still need this? Okay, I will do that.
Oh, I'm good with that.
Oh, you're good with that.
I thought you meant like first.
Oh. You want to pass that back? All right, so then surface area of parametric surfaces is the last thing. And the derivation will not be nearly as long. But imagine again that you have some surface. And on the surface, we have a point. Let's say those coordinates are r of u sub k, v sub k. And we're going to approximate, so just like we did earlier, we're going to approximate the surface by kind of inspecting one of these little patches. Okay? And if I magnify that patch, so let's make this a little larger. Here we have a U curve. Here we have a V curve. If I use a tangent vector, we'll get there. Let me actually use blue here. And then I get a tangent plane. Okay, and we can approximate these vectors by calling this partial r partial u times change in u, so delta u sub k. And then this side of the parallelogram will be the same thing, partial r partial v, delta v sub k. And if you remember what we did earlier, we wanted to find the area of these little parallelograms so that we can kind of make them smaller and smaller so that that area would eventually represent the area of the whole surface, right? So how do we find the area of this parallelogram or rectangle if we have the sides in terms of vectors? Take the cross product magnitude. Good. So we're going to say that the area is approximately the magnitude of the cross product of partial r partial u delta u sub k with partial r partial v delta v sub k. Now, since these are just constants, we're going to do some grouping here. Keep this as partial r partial u cross partial r partial v, and pull out delta u sub k delta v sub k. The area is approximately this, which is equal to that. So it's not like this is approximately this, it's the same, right? So now this equals the same thing, but another way of writing delta u sub k delta v sub k would be to say that that's dA or delta a sub k, just like we did before. So then if we take the limit as n approaches infinity of the Riemann sum from k equals 1 to n of all of these little areas, then this actually becomes the formula for surface area. Surface area will be the double integral over the region R, and here we'll just have magnitude of partial r partial u cross partial r partial v dA. So now we have another option for finding surface area. If it's in terms of rectangular coordinates, then you can use the formula that we derived earlier in the unit, which took a considerable amount of time. Or if it's in parametric format, this would also give you the surface area if you don't want to like convert it back to rectangular. Okay. So I'll leave it up to you. Is this formula self-explanatory, or do you want to go through an example? Example? Okay. So this will be the last thing we do today, and then I'll go over any questions you guys want, or just give you some time to keep working on homework, and we can go over stuff tomorrow. Okay. So let's say we want to find surface area for cone where x equals u, y equals u cosine v, and z equals u sine v, where u is from 0 to 2 and v is from 0 to 2 pi. So I don't know if you remember, but yesterday we talked about equations that look like this. What would the axis of revolution be here? X. Our function that we're revolving around the x-axis would be u, which is really just x. So y equals x, right? So you guys see why this is a cone. So if you actually sketched it, y equals x looks something like this. You're revolving that around the x-axis. Do you guys see the cone? Wow, that was really bad. Let's pretend I didn't draw that. We'll just hide that. Okay. We can still do the calculus. How do we find the surface area? We have our bounds, right? The only thing we have to worry about is finding this magnitude here. So first, let's find the partial derivatives. What would partial r partial u be? One cosine v sine v, yes. And then partial r partial v would be
0, negative u sine v.
and u cosine v, right? So now if we find the magnitude of the cross product, we're going to get what? That times that is you just get a u out of there?
Yeah, sine squared plus cosine squared.
Okay. What's the next component? Negative u cosine v. And the last one would be? Good. So now we want to find the magnitude of that still, right? Which would be the square root of u squared plus u squared cosine squared v plus u squared sine squared v. If you factor out a u squared from the last two terms, you just get u squared plus u squared, which is 2u squared, so this is just root 2u. So then the integral, pretty easy to work with. double integral of root 2u. Let's say I go du dv, and we just plug in the bounds for u, which is from 0 to 2, and then 0 to 2 pi. So root 2u, when you integrate, would be what?
Which over to
And then plug in u equals 0, u equals 2, and what do we get? 2 root 2. That's going to be 2 root 2v from 0 to 2 pi. So we just get 4 pi root 2. So that would be the surface area. Okay? All right. We have about what I said we would have, 15 minutes.